So, CogX is a conference about artificial intelligence. I realize that not all the panels are about artificial intelligence, but I try to do something that would be at the intersection of the topics of blockchains and artificial intelligence. And what I'm going to present is actually mostly a negative result. I would love to come out and tell you, like the combination of those two things is great. But in fact, we're going to look at the intersection and wonder, is there anything in the intersection? I think there is, but I think there's not as much as what people think. So I'm going to start by defining a little bit what I think of in terms of blockchains. I also, I will look at some ideas from AI and whether or not they have some meaning in our world, and then look at a bit at the intersection. Okay. All right. So word of caution, both artificial intelligence and blockchain are fine technologies. They do their job very well. They're both very interesting. They both have useful applications, especially artificial intelligence. Blockchain is still a bit out there. Jury's not completely out on that. But both of these attract empty hype. And what's more, the combination of this is a nonlinear effect where you combine both and you have the worst of both worlds. It tends to attract a lot of empty ideas. It's kind of a beacon. So, if someone out there is looking at the title of my talk and is thinking like, oh, Arthur's talking about blockchain AI, he must, that must be bullshit. I urge him. I hope they will listen to the talk and say like, no, this is a negative result. So what are blockchains? So a blockchain is first and foremost a data structure. It's basically a linked list of blocks which contains operations, and every block contains a hash of its content and the block before. A blockchain is a data structure. It's not an algorithm. It's not a protocol by itself. It's a data structure. Now, a corollary to that is that you should never say blockchain without an article. If you hear someone say, oh, we're using blockchain, that's the same way of saying, like, how do you get around? I'm using vehicle. No, it's a vehicle. I'm using a vehicle to get around, or I'm using this vehicle to get around. It's not a technology. It's a data structure. Now, it is used to facilitate peer-to-peer protocols, in particular when you want to maintain a decentralized, mutable singleton. And what I mean by that is you have a bunch of participants on a network and they want to maintain a state. Like, for example, a ledger would be the most useful example because that's how you build a cryptocurrency. So you have these participants, they want to build, they want to have this mutable state, they want to have a singleton. They all want to have the same view of the ledger, because a ledger where everyone has a very different vision of what the ledger is not particularly helpful. And if you look at that and you see the word mutable here, and you might be shocked, you say, what? What do you mean mutable? I read somewhere that blockchains are immutable. Isn't the whole point of blockchain immutability? Yes, a blockchain is an immutable data structure, but please do not reason by just using words and saying like, oh, is it mutable, immutable? No, a blockchain is an immutable data structure, but the entire point of the exercise is to have mutation. If you don't have, if you have a ledger and you do a transaction in a ledger, that's a mutation. I had tokens. Now you have tokens. You've made a mutation. Now the difficulty is that if you want to have a distributed, decentralized system where you have mutations, it's very hard, because who can edit what at what time? If I have a database on my computer and I want to change it, I just go in and I change it. The database is in one place. It's very easy. If the database is distributed over a giant network, it's really, really hard. Who's going to edit it? How do we make sure that everyone sees the exact same edits? And the trick of using a blockchain is that essentially you represent this mutable state with an immutable structure. So you start with what you call a genesis block, which really should be called a genesis state. It represents the initial state at the beginning of time. This is S0, the state we start with. And then you keep adding blocks, and the blocks represent transformation. So when I add data, in computer science, we talk about immutable data structure or append-only data structure. It's the same thing, because if I just keep adding data, I'm not modifying what was before, I'm just adding more. So I add blocks, and now, I add a block 1, so I move from the genesis state to the state A, and I add a second block, and now I'm in state B. So this state can change progressively as we add blocks to the system. That's the entire point. Now the difficulty is that in practice, since it's a distributed decentralized system, you don't in general have only one block. Maybe two people could create a block. You could have block 2 prime and block 2. And those blocks would correspond to different states. One would be state B prime and state B. So we haven't really fully solved our problem because we still have this idea that somehow two people could edit the state and they would have two different versions. However, we have greatly simplified the problem now, because instead of having kind of a free-for-all where anyone can edit any part of anything, now we've reduced the problem of mutation to that of picking the right end of the chain. You can imagine this, the chain as a giant spaghetti, and you're just like trying to grab the end. And so consensus, the idea is that you have a singleton that everyone is saying the same version, can be collapsed into thinking everyone has the same hash for the end of the chain. That's a much simpler problem conceptually to work with than the general problem of doing edits everywhere. So it's a data structure that makes your life a lot easier. It's a data structure also that's self-authenticated. It has a lot of very, very nice properties, which makes building this peer-to-peer protocol easier. So what defines a blockchain protocol? I've talked about the blockchain as a data structure. What is a protocol? Well, the protocol is defined by a rule set. And the rule set is, basically, it consists of two things. One is what constitutes a valid block, or equivalently, what constitutes a valid state transaction. For example, it's interesting that in typical cryptocurrencies, I don't have the right to spend your coin, right? So not every transaction, not every state transition is possible. We define the state transition that we allow and the one that we don't allow. So that's part of the rules. And that's I would say that's the bulk of it. And then the second part of the rules is how do we grab the end of the noodle? How do we know that we're all using the same block at the end of the same chain, that we're using block 2 and not block 2 prime? And that's consensus. And really the interesting idea in using blockchain for decentralized consensus is that you can tie pecuniary incentives to everyone grabbing the same end of the same noodle. So what you do, for example, in Bitcoin is you use a proof of work and you say, well, the rule is that whichever branch has the most total hashing power is going to be the canonical branch, the branch that everyone is going to agree on. So that's a decision, that's a way of making a decision. There are other techniques out there for consensus. Proof of stake is now becoming increasingly popular, and the idea of proof of stake is that you ask the people who actually own the underlying cryptocurrency to collectively decide on which branch should be the canonical branch. So those are different techniques, but that basically that is basically the definition of a protocol. All right, so now I'm going to do a little detour around AI and what can we learn about AI from AI. So the first thing is that it's hard to learn anything from AI because it's not a single there's no single unified field called AI. There's a lot of very different problems that you meet in AI. You could be doing search, you could be doing perception, you could be looking at logic and theorem proving. There's of course statistical learning is now the bulk of it. There's planning, especially if you're doing robotics. So many different problems, and they're all kind of trying to do the same, to get at the same thing, but they are quite different problem when you study them. And the tools you use to address those problems, they're even more different. You start with the first attempts at AI with backtracking, constant propagation, and then now a lot of AI around machine learning, statistical learning is going to be focused on gradient descent and optimization as a tool. We have genetic algorithms, kernel methods. So all these tools are very different. So saying that we're going to learn something from AI, given that it's so much different problems and so much different techniques, is really difficult. It's not like you can really abstract an essence out of all of this. However, if we had to draw one lesson, just like one lesson from the field of AI over the past 30, 50 years, is that learning seems to be the most successful lesson. And by that I mean, you do not attempt to design every aspect of the system a priori. Because the first attempts at AI were basically saying, we're going to study the problem completely, and then we're going to come up with a solution for the problem, and we're going to implement the solution. And that sounds a little like people wouldn't even think of AI today when they look at those systems like expert systems, but they were AI. And so the image here is the goddess Athena being born out of the head of Zeus. And when she's born, she's already fully grown, and she's all clad, and she's wearing her armors. So it's kind of the idea is that out of your head the perfect solution is going to come and solve everything. And so the lesson is that you can't really do that. What you should do instead is you should learn the problem. You should have open principles and use those principles to gradually gather experience and improve yourself over time. And so when you put it together, in terms of blockchains, what that would mean is do not try to design the perfect rule set a priori. Do not start with just one rule set for your blockchain and say, that's going to be it for the next 100 years. This is exactly what we're going to use, and we're never going to change our rule set. Now, it's important for the values of a blockchain not to change over time. You want to preserve your values, otherwise, you're just going to go anywhere. But you want to maybe have some flexibilities in your rule set because there are some rules which can be more efficient than other rules. And I'm not talking about, I'm not talking about saying like, oh, we had a rules that only you can spend your coin and now it's someone else. That's a stupid change. I'm talking about subtle rules in such as how do we actually encode transactions? How do we actually, what cryptographic primitives do we use for that? How do we do consensus? There's a lot of technological problems which can be encoded as slight change in rule sets. And if you don't have a way of improving your rule set, then you basically have to get it right in the first time. You have to have Athena come out of your head perfectly formed. So in practice, what I would suggest is you can abstract the rule set as a set of pure functions. So you have pure functions that represent the behavior of your system. And then you introduce reflexive self-amendment rules. So basically, your rules provide for a way of modifying themselves. And you'll see the big Tezos logo. So this is a plug because Tezos is a project I've been working on for the past 4 years. It's a big proof-of-stake blockchain that's been live for a year. And that is basically exactly what it does. It's the self-amending blockchain. So the idea is that it incorporates in its rules a way of changing its own rules. And the point of that is the realization that fundamentally, you don't know exactly what the best rule set is going to be 10 years from now. So instead of designing this perfectly, you design a system that's capable of learning and recursive self-improvement. Thank you. So how AI-ish is this? Well, there's a general idea in this whole thing, which is very AI-ish in nature, which is recursive self-improvement with code reasoning reflexively about itself. There's not a whole lot of that today in modern AI, but if you look at the philosophy of AI, it is one idea which is pretty central to the, which is a pretty central and recurring theme. However, reflection, in Tezos, for example, is currently limited to something very simple. The way reflection works is the rule is to look at a new piece of code, hash it, and you compare the hash with what humans have told you that they want, and if the hash matches what human wants, then you accept it. So there are humans in the loop. However, it is recursively self-improving, so in theory you can get it better and better and better. So for example, you can have rules that say, we don't want to modify this part of the code, or you can have rules that say, when the code comes, it needs to come up with a formal proofs that certain properties are verified. So gradually you can take the humans out of the loop by introducing better and better rules. And I say a big but as well because concepts that rhymes do not necessarily connect on a fundamental level. It's one thing that I often see. You'll see it when people tout supply chain solutions for blockchains because they will say, in blockchains you can track where the coins are coming from, but we're interested in tracking where letters is coming from. What if we connected blockchain and letters? And that's something that only works because it's using the same words, but that doesn't actually work in practice. It's not it's not a good use. So I am very wary of just reasoning by analogy as opposed to reasoning from first principles. But I do think that there's something AI-ish about this approach. There's a really cool paper in AI called The Gödel Machine by Jürgen Schmidhuber, which talks about specifically an AI agent that iterates through every rewriting of its own system and every proof. And if it finds a rewrite of its system alongside a proof that shows that it gets it closer to its goal, it will apply it. And you have, the nice thing about that is that you will have proofs that it is in some sense optimal. The bad thing is that you have gigantic constants if you want to actually make this work. So it is a bit impractical. So aside from this, why are AI and blockchains kind of like oil and water? Well, the problem is the rules that you use to create a blockchain, they need to be very predictable. You need to know exactly what's going to happen when you touch the system, and they also need to be resistant to adversarial inputs. A lot of this is there are people who are going to try to trick the system into doing bad things. They're going to try to DOS it. They're going to try to get invalid things in there. And most modern AI techniques today are not focused on this at all. They're actually pretty bad. There's really interesting research on doing AI with adversarial inputs, but right now it's not, like the resistance to adversaries is not very, very good. And so if you try to inject AI inside of your blockchain, you really are going to have a bad time, because the whole point is that we want to make, when you do accounting, you want to have accounting be more math-like and machine-like. You don't want accounting to be human-like. And a lot of the efforts right now is to try to make machine human-like. So it's kind of the opposite trend. No matter how cool AI and blockchains are independently, they don't necessarily mix very well. But what about blockchain-based data marketplaces? So that's one pitch you'll hear. It's like, no. Of course, we're not going to use AI for a protocol, but AI marketplace is a cool idea, and we're going to use the blockchain for that. So the idea behind this is to say, okay, a lot of AI capabilities today, they don't necessarily come from algorithms. A lot of that is published research. They come from having these big private data sets of user data. I don't fully agree with that. I think there's a lot of gains to be made from better theory and better models, and I think a lot of people in the industry agree with that, but it's still a popular idea that it's all about the data sets. The second thing is, well, what if we what if instead of this data being siloed inside this like web giants, we crowdsource the data and then we will pay people to produce the data? So far, so good. And then you have a leap of faith, and then blockchain. And so, in general, a data marketplace is not necessarily a bad idea. If you want to buy data from people, why not? And if you want to pay people with cryptocurrencies, there's nothing wrong with that. What doesn't make sense is trying to shoehorn the whole process inside a blockchain besides making a simple payments. And I think part of the reason that people are attracted to this is that they look at cryptocurrencies and they're like, oh, wait, it's digital and it's scarce. But how can we make digital scarcity? Can we make digital scarcity about data? Not really. The whole point of it, the reason that a Tez or an Ether or a Bitcoin are scarce is because they represent agreement. I own this cryptocurrency and everyone agrees that I do. And that is the thing that is scarce. It's the agreement. It's not the digital representation itself. Whereas for data, the data itself is valuable, right? So if I have a piece of data, it does not matter one bit that people agree that I legitimately have access to the data. As long as I have access to it, I can use it. And so I think in general that data marketplaces might make sense, but I don't really think that they have anything to do with blockchains. And so it's a tempting pitch, but I personally don't think it makes a whole lot of sense. So what does make sense? Are there intersections? And I would say that the intersections are going to be at the periphery. It's when you use AI as a tool around blockchain. So we've mentioned UX. If you're using your AI to tweak your UX, A/B testing doesn't sound like AI, but it is a bit of AI, and especially if you try to cut down on your search space for A/B testing. So, like using AI for doing better A/B testing for your UX, that's fantastic. Other ideas: client-side fraud and prevention. You've seen in Argent, for example, this very nice feature where you will have a daily spending limits. What if it's and today, if you have your bank is going to detect fraud. What if your wallet can do that? What if your wallet tells you, hey, it doesn't look like you're using your key with someone you usually transact with. It looks like something is off. Are you really sure? Let's ask for more confirmation. So that's a very interesting use by analyzing the transaction patterns. Automated theorem proving for formal verification of smart contracts. So right now we have today smart contracts which hold hundreds of millions of dollars, and they're written with the hopes that they don't have bugs. And as we know, sometimes they do, and a lot of money is lost to the smart contracts. Formal verification is a mathematical technique where you can check that a program corresponds to its specification, and it's not completely foolproof. So you can still have bugs, but it's a lot easier to not have bug in your specification than it is to not have bug in your implementation. And so in practice, it does cut down a lot the number of bugs. Now it's a manual process. It's not very easy, but there are a lot of research into using AI techniques for doing better formal verification or even program synthesis from smart contract specification. Fantastic use of AI in the context of blockchain. Absolutely fantastic. And a third one, which I find particularly interesting, is we have a lot of new consensus algorithm, and even though historically the study of consensus algorithms is based on having honest actors versus dishonest actor. Classical BFT, you will say, I have 2/3 plus 1 of honest users, 1/3 minus 1 of dishonest users, and I prove that I can still, that I can reach agreement in presence of Byzantine actor. In decentralized networks, it's a little different because honesty is being incentivized by pecuniary means. And so a more interesting question is to say, what is the cost of bribery in a system like this? Or if I'm honest, but I don't try to collude with other people, what is the optimal strategy for me? Is the optimal strategy to follow the honest strategy? As we know in Bitcoin, a very influential paper in Bitcoin has been the Bitcoin selfish mining paper. And what the Bitcoin selfish mining paper showed is that if you're a Bitcoin miner and you're completely rational and self-interested, you might try a different strategy. You might deviate from this strategy. So one way of automatically discovering these deviant strategies is through reinforcement learning. You can run simulations of blockchain environments with a lot of agents, and you try to teach those agents block creation strategies that are trying to maximize the amount of money that they extract from the system. So that's an interesting use of AI. All right, so this is my time. If you have any questions, come and find me after. I am at Arthur B on Twitter and on Wire if you want to reach out. Thank you.